Hard to believe, but we're at the end of week 5 today, and this is geometry. We've been talking this week about triangle similarity. On Tuesday, we talked about the similarity proofs: angle, angle, side, 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 angle, side. Different a little bit than what you saw with the proofs for congruency, because there is no angle, angle proof for congruency. It's only for similarity. So there was a graphic example in there of how to keep those separate with some filled in examples. So if you didn't make it here on Tuesday, then check out the video when I get it posted tomorrow. Tomorrow's Friday. Yeah, I'll get it posted tomorrow, because that's all in there. The part we're going to get into today starts off with something called the proportionality theorem. And again, we're dealing with situations involving parallel lines. Funny how that comes up so often. And right at the beginning of the description here for proportionality, it says, if a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides into segments of proportional lengths. Okay. So when we talked about initially whether or not we could determine if triangles were similar, what was the setup for that? It was whether or not they're proportional, right? They have to have the same angles, identical angles, and all the sides must be proportional. So this is just a variation on that. This is not a mid-segment situation, and you can see from the drawing even that this DE line is not in the center of either of the two sides. It's not connecting the midpoints. So we're not talking about creating congruent segments on the sides of the triangle. We're talking about creating two proportional triangles. So here's what that looks like when you fill in the blanks. And the key there to remember is these little arrows again. That tells you that those lines, those segments, or those sides of those triangles are proportional. So the first, we've got an if-then statement, which is kind of the way a lot of proofs start. The two parallel lines are identified there in the first if statement. Then it gives you the proportions. BD over DA is going to be proportional. It's going to equal BE over EC. The converse just means you turn that thing around, you turn those two statements around. If you have proportionality, then you can prove that the two line segments are parallel. So it's not terribly complicated. The key to all this, though, is remembering how to set up these problems. You know, what are you actually comparing? So if you look at those first two problems there, it gives you the setup exactly like this description. You've got this segment here of the top side compared to the second segment on top. And just like we were doing with the original ratios and proportions, we were doing, if you started off by comparing the smaller to the larger triangles, then the smaller numbers are always going to be on the top of your proportion, your ratio, and the larger triangle numbers are going to be in the bottom. This kind of follows a similar pattern. The two segments on the one side are going to be together. And whichever one you start off with on top, when you go to the other side, you gotta take the corresponding segment that's across the other side of the triangle. 14 is to 12. And so when you look at the tops of both of these ratios, 14 and x go together. The bottom, 12 and 15 go together. From there, it's just cross multiplying. Everybody remembers how to cross multiply and solve proportions, I hope. 14 times 15 is 210. 12 times x is 12x. And you get x equals 17.5. Variation of the same problem is in number 2. Only this time it's kind of flipped over. It's showing us the 18 compared to x. So we get 21. Again, this little segment here, it has the 18 with it. This little segment on the other side is 21. So those both have to be compared to each other on the top. The bottoms become the other two pieces of that triangle. You got some big numbers on that one. So make sure you get this part of your notes filled in so you've got these comparisons and can refer to them later. Okay, so let's look at a couple of these problems to see if we can do the setup and do the comparisons. Because the only thing that they're going to try to do with these proportionality problems is make it look more difficult. But if you remember, the first ratio always includes the two pieces that are on the same side being compared to the two pieces, the corresponding two pieces on the other side. The setup is easy. So what do we need to be able to solve question number 3?
What goes with x?
Yeah, but aren't we missing something else?
No, we're missing what goes with x.
Right, but what about this little segment right here?
That's what I'm saying.
Okay, well, how do we find that?
Would you take 55 minus 45?
That's exactly what you do, Jonathan. Perfect. So we'd end up with 10 compared to 45 equals x compared to 36. So 360 equals 45x. I'm kind of going out on a limb here to see if I've got it set up correctly. I think I do, because the 10 and the 45 are the segments on the same side. So I had the 10 on the top, which means on the other side, I'm going to put the x on the top. So 45x equals 360. I got x equals 8. Let's see how I did. Whew, good. Problem 4, very similar. You know, and they've got these other numbers in here showing you the whole length of that side to kind of throw you off. Because we're not comparing 55 to anything. We're comparing these two segments here. 10 gets compared to the x. 45 gets compared to the 36. So that's why those numbers, the big segments from one is on the bottom compared to the big segment from the other side. All these are going to work that way. 4 is the same way. We got to figure out this missing number here. 27 minus 6 gives you the remaining 21. Not much else to it. So let's let's try a couple of these algebraic proportions to see if we can get those set up correctly. How would you set up number 5, for instance? Anybody have an idea?
I was late. There was road construction on 19.
I'm going to pause this for a second, you guys. You all think about that question. Okay, so with any of these problems, remember what we're talking about are proportional lengths that are on the same side of the triangle being compared to the proportional lengths on the other side of the same triangle. So if you go back to your original, this is why I keep saying keep your notes handy, because every one of these problems is going to fit this pattern right here, this BD over DA. That's the two sides, or the two segments that are on that same side. So the short segment over the long segment, and then you set up the proportion involving the same thing, short segment compared to the long segment on the other side. So how do you want to start? You want to start with the 30 or with the x plus 7? Okay, so we're going to take a minute here and try to solve a couple of these problems on this Jamboard that I just created. All comes down to the setup, just like seemingly every other problem that we've done in geometry. The fact that there's an algebraic expression there doesn't change anything. When we were looking at the actual formula for these, remember, short side to long side on the same side, short piece to long piece on the same side. That's what they're showing you here with BD compared to DA. That's the proportion of these two triangles. They're saying this triangle here, this little one, is proportional to the big one. And we get the sides that are proportional in also. So if you follow this pattern, and it is a pattern that allows you to solve any proportionality problem like this, just follow the pattern, plug the stuff in. So on my Jamboard, these are the numbers on one side that I'm going to compare in my first ratio. And I'm just going to go ahead and put the 30 on the top, x plus 7 on the bottom, and make it equal to the numbers from the other side. Now, what goes where in my other ratio? Where do I put the 25 and the 15? Which one goes on the top?
They're corresponding with them.
25, right. These correspond and these correspond. So you want to put them in the same relative positions when you set up those ratios. all these problems are going to be just like that. So number 6, I got 6 is to 21 as x minus 1 is to 3x plus 1. You know, they could have just done this all with numbers, but they can't do that. Of course, they got to try to make it more difficult. Now you got a proportion set up and you know already how to cross multiply and solve proportions. 30 times 15, I think it's 450. Yep. It's dangerous when I try to do multiplication in my head these days. Make it equal to the other one. When you do that cross, though, now you got a distributive property to deal with because it's 25 times that whole expression. Same thing over here. We're going to get 2 distributive property problems out of this one. 6 times 3x plus 1 is going to equal the other cross, 21 times x minus 1. Now it's just like solving any other algebraic equation, right? Get the x by itself. On problem number 6, you've got the x variable on both sides of the equation, so you're going to have to gather those up on one side or the other. So what do we get for x on number 5? So this will be 450 equals 25x plus 175. Subtract 175. So 275 equals 25x. How many times does 25 go into 275? How about 11? 8 times 25 is 200. So 3 more gives you 275. And that's what you're going to have to do to be able to solve these problems for x. You know, because we're not talking about angle measures on any of these. It's all side lengths and dimensions. So x, when x equals 11 on this problem number 5, that replaces x plus 7. So this proportionate side now we know is 18. 30 is to 18 as 25 is to 15. So once you plug that number back in and actually know that that equals 18, now you've got 2 ratios that are equivalent. 30 over 18 can be reduced to the same number as 25 over 15. Because that was one of the tests that we did Tuesday, just to even to figure out if something is proportional, right? Does it reduce to the same scale factor? So go back to my original and plug that 11 in here. 11 plus 7 is 18. What do these both reduce to? What is the scale factor? Should be equivalent. What's the lowest terms for 30 over 18? You guys remember how to reduce fractions, don't you? That's all I'm asking you to do. Tell me what that reduces to.
would answer, but I'm driving, so
Okay, what's the greatest common factor between 30 and 18? 2 goes into 30 and 18. 3 goes into 30 and 18. Does 4? No. Does 5? Yeah, in 30, but not 18. What about 6?
yeah.
Divide them both by 6. That's all we're doing. We're reducing fractions. What do you get when you divide 30 by 6?
5.
And divide 18 by 6, 5 over 3. The other one, they both end in 5, so obviously you need to divide them by 5. Any number that ends in 5 is going to be divisible by 5. So 25 divided by 5 equals 5. 15 divided by 5 equals 3. And that last step, what I just did, that is the way that you can check your work to prove to yourself that you've done these correctly. If your setup is correct, you're going to end up with 2 equivalent ratios, 2 equivalent fractions. Every one of these problems works that way. Questions on any of that? All right, well, let's go back to the handouts here and see what's next. Now, this next page, the top of the next page, gives you some more graphic examples. We're still talking about similar triangles. Now we can start looking at corresponding parts being proportional to the corresponding sides. Okay. Well, that first example there, it looks like we've got a couple of right triangles. The second example looks like a bisection. Why would I say that these two, at Q and at U, why would I say that those look like they're being bisected? Remember the definition for bisect, it cuts something in half into 2 equal parts. So aren't they showing that this angle here and this angle on this side are congruent with that little half circle? Yeah, absolutely. That's why I said they're being bisected, because it's created two. That's the only way to get 2 equal angles out of that. So this is another example here of where you got to remember what this symbolism is here when you see these little half circle marks inside some angles, or when you see the tick marks here, like on the third example. So this HJ line here and the LN line on the other smaller triangle, what are those lines doing to those baselines? It's another bisection, right? It's connecting to the midpoint. How do I know that? Well, because now I see here, because of these tick marks, I've got 2 segments that are identical. Those are congruent. That's what the little tick mark means. So this is another part of your notes that you should have completely filled in. And I gotta go ahead to it. Here we go. And some new definitions are popping in here. The altitude. You can probably tell that from the drawing. you look at this line here, BD and FH, an altitude is a line that is struck from one angle and intersects the opposite side of the triangle at a 90-degree angle. So they're showing us the square here on this angle BDC. We also have a right angle at BDA. Both sides of that line BD are creating right angles. They have to. They have to, or that original triangle wasn't actually a triangle. It was some other shape. And so the pieces and parts here are going to correspond. You've got to visualize this a little bit differently. And these ratios are the ones that you're going to need to work with. So where's BD? Okay, BD corresponds to FH. Okay, well, those are the two altitude lines, the vertical lines that are going from angle B and angle F straight down to intersect with the base of each triangle. Okay, so now we know, because of that, we can set up this AB side is proportional to EF. That's the comparison we're making. So now you're not working with pieces of the same triangle, you're working with corresponding parts of two different triangles. The altitude line corresponds in both of these. This left-hand side of both of these also correspond. That's why we can compare the altitude lines and those two left side lines. Same thing holds true in these other examples. We got bisectors here, so QS, our bisection line, is comparable to UW, which is the bisector on the other triangle. And then you can pick QP is going to be in comparison comparable to UT, or you could say QR is going to be comparable in corresponding to UV. PS corresponds to TW, SR corresponds to WV. Any of those parts that are created when you bisect a triangle like that are going to end up being corresponding. You can establish those ratios. Median works the same way. You're just cutting the baseline into two equal parts. So the median line, HJ, and LN are what you're comparing. And then this picking this left-hand side, GH to KL. So you need those drawings and those ratios, get them in your notes. Because the problems that you're going to be asked to do are exactly from that. So if you look at the first problem here below that, which one of these first three examples does that fit? Is it a problem involving altitudes, angle bisectors, or medians? This is basically pattern matching here that I'm talking about having you do. Because there's a pattern to solving all these problems. What pattern does the problem number one fit?
Medians.
Median, yeah. It's a no-brainer. When you see these tick marks here on a line, that's because of this thing here, this line coming down and splitting that line into two equal parts, it has to be a median. Because a median is the same as a midpoint. It's hitting the midpoint. So it's automatically creating two equal lines. So now that you know that WS, which is X, can compare to DF, which is 15, is following this exact pattern. The median lines compare to each other. Let's see, what are we can pick one of the other ones. 20. Okay, 16 is on this triangle where so we had X on the top, so we got to put any other values from this left-hand triangle on the top also in our ratio, and then pick the correct side that corresponds to that from the other triangle. So that goes on the bottom. We could have used this other side. We could have used 19.2 here instead of 16 and compared it to the 24. Why didn't whoever did this teacher's guide, why didn't they do that? It's not a trick question. I would not use that. You want to mess with that 0.2 when you're cross multiplying and you got your problem set up and you've got 19.2 as a number to work with? No. Pick the easy one. 16. It's a whole number. Start throwing decimals in here. Never know what you're going to end up with. It just complicates things, and it creates another potential spot to make a mistake. So now we know problem number 1 is a median problem. What about number 2?
Altitude.
Yep, it's altitudes. And essentially, if you can match up the kind of problem, you've got the pattern already. So let's see, 1 is the median problem, the pattern. 2 is an altitude problem. 3 is the other example. Remember what it's called? What do these little lines in here mean? What do these half circle lines mean?
Angle bisector.
Yep. We are bisecting those angles. That's right. So that's the bisection angle. And you're going to follow the same pattern. Compare the bisect lines, QS and UW, or whatever they're labeled as, 32 to 24. And we only have one other side identified, so we're going to compare AC to EF. Pretty confident about that. How do I know which sides to pick? Like in that first problem, how does even with that 19.2 there, how would I know which other side to pick? Now, this median line, that's easy because I know it has to be the median when I see those two congruent pieces come out of it. How do I know to pick the number 16 and the number 20? How do I know that those sides correspond? Oh, wake up, you guys. Come on.
Because of the tick marks?
No, I'm talking about these other sides here, the other numbers. What is this that I've just highlighted? What does that tell us?
That they're similar.
Yeah. And what's important about the lettering and the order?
They're
Similarity statement. So why do we care?
because they're congruent.
No, not congruent.
with each
Similar,
other.
proportional. Look at this similarity statement here. STU is similar to triangle DEC. Where's the number 16? What side is it associated with?
S and T.
ST. And where is ST in the similarity statement?
DE, or not the beginning. So it would be the similar one would be DE.
DE, right. And remember, we've talked about order being essential for these similarity statements to help us, because I absolutely know that the side of this triangle ST corresponds to the DE side of the other triangle because they're in the same position. ST is in the first two letter positions for the one triangle, and DE is in the first two letter positions in the other triangle. If you don't pay attention to that similarity statement and the order of these letters, you're probably going to pick the wrong numbers, because you got to get the ones to match up that are corresponding. Same thing in all of these. GH, ML. So JH is our altitude, but GH and ML correspond. What numbers do we have here? We have JH and LN numbers. Where's KL? Okay, KL is the second and third letter in that one. So HI has to go together in the other one. Might seem obvious because that's where the X is. But it wasn't obvious on that first one, because now we got two different sides to choose from. So remember that the similarity statement works exactly the same way as a congruency statement. The order of the letters tells you all about the corresponding parts between the two triangles. So if you look here at problem number 5, what kind of a problem is that? Which one of those patterns would we be looking at? Is it an altitude, a median, or an angle bisector?
Median.
Yep. So the median lines are going to correspond. YM is going to correspond to LX. And YC, second and third letters, going to correspond to LH, second and third letters on the other one. Questions? Anybody? So here's the next section here goes into some more detail about triangle angle bisectors. The bisector is going to separate the opposite sides into segments that are proportional to the lengths of the other two sides. Seems like a mouthful, but what that boils down to is this set of ratios. We don't have to worry about BD. That is our angle bisector line. If we were doing a proof, we would say this is a reflexive property situation because it's equal to itself. But the other sides now we can say are proportional. This segment here, AD, is proportional to this one. And the ratio for the other two sides follows the same way. Here we had on the top is our segment from the left-hand side of this triangle. On the bottom is the segment from the right-hand side. So you got to do the same thing with the other two sides. Make sure you get those in the correct location, top or bottom of your ratios. Once you've done that, it's just like every other proportion that you've ever solved. Cross multiply, solve for the variable. Okay, so the next section in your packet is a big shift. Talks about something called dilations. If you've ever gone to the eye doctor and they put drops in your eye and they dilate your pupil, what does that mean? Well, on a bright sunny day, your pupils are small. Well, the doctor puts the drops in there and your pupil gets big. A dilation is either a shrinkage or an enlargement of a figure. And all of these are going to happen on an XY coordinate plane. So now it's going to check your ability to remember how to graph, one, and how to use the scale factor. Because scale factor is how the transformation, the dilation occurs. If you're making something smaller, the scale factor is going to be a fraction because it's going to be less than a 1-to-1 ratio. You're making something bigger, you're going to multiply by, it might still be a fraction, but it's going to be a number that's greater than 1 because you're enlarging it. And that's what they mean when they talk about this letter K. K is our scale factor. So really important that you get these in your notes here also. When K is greater than 1, the dilation involves an enlargement. When K is less than 1, the dilation is a reduction. So that's when you're shrinking something. And the way these problems are set up, they give you coordinates. And problem number 1 says triangle RST has vertices at R, S, and T, and they're giving you the 3 ordered pairs that correspond to each corner of that triangle. And it says the scale factor is 2. So is this an enlargement or a shrinkage? What's that?
Enlarge.
Yep. There's no guesswork in this, guys. If it's greater than 1, it's an enlargement. That's why I just said, get this in your notes. So how do you work with that? Well, RST are the original vertices, and you see this other list down here. R with an apostrophe, S with an apostrophe, T with an apostrophe. You can call those R prime, S prime, T prime. Take every one of these ordered pairs, multiply every number by 2. That's going to give you the new ordered pairs that now you can plot. You can graph it out. So for this first one, when my scale factor is 2, R prime is going to be -10, 2. For the second one, it's going to be -6, 8. For T, it's going to be 4, -2. And that's the easy part. Then you got to graph it. And right there, you can see how it's gone from the original small triangle RST to the enlarged version. And if you compare these numbers down here, R prime, S prime, T prime, it's just what I said. Every one of these originals multiplied by 2. There's really not anything more to this. If we were shrinking something that's large down to a smaller size, you do exactly the same thing. Like problem number 3 says it's a rhombus. So it's got 4 vertices. The scale factor is 1/2. So we're going to cut every one of those ordered pair numbers in half. So the vertices at letter J prime will be -5, 1, right? Half of -10 is -5. That's all there is to it. We're shrinking that rhombus. Every one of the values from these ordered pairs, the original ordered pairs, also shrinks by that same amount. The scale factor is like a multiple. So if it's less than 1, we're shrinking. If it's greater than 1, we're doing an enlargement. Anybody have questions? Okay. Now the only thing that's left in here is the study guide. Do you remember how to find the scale factor? Okay, well, if you don't, that could be a problem. How would you find the scale factor on problem number 3? Aren't we comparing the sides, the dimensions of the corresponding sides between the two shapes? So what numbers do we want to compare? Does the 36 go with the 14 or the 20? Well, this is going to be a tough test for you guys if you don't remember this. And for this problem with the scale factor, we don't have a similarity statement. Obviously, they're not congruent because they're not the same size. So you have to use visual cues. Which side of triangle B goes with the 36 from triangle A?
20?
It is 20. Because got to remember, guys, when if all you're trying to do is find a scale factor, you got to pick the corresponding sides and compare them. So if I'm comparing the larger triangle sides to the smaller triangle sides, that's the ratio I'm going to create, which means that this 25.2 would also have to go with that other side here. Those two go together also. So 36 over 20, that's reducible. 4 goes into both of those numbers. It should get a scale factor of 9 over 5. Now the other one has a decimal in it, so it's a little bit trickier. Which is why I chose not to use it to begin with. So if we're taking this smaller triangle and we're going to blow it up to this bigger one, we're going to use a scale factor on this one. We would say K equals 9 over 5. Could I also do it the other way? Could I put the smaller over the larger? Well, yeah, of course. And all that is the inverse. So now you could say that the smaller triangle is 5/9 the size of the larger one. So that's how the scale factor works on this. So what is there in this unit? What have we done? Maybe 4 things. Similarity, setting up those proportions, remembering how to use these similarity statements, like this one in number 5. Triangle KLJ is similar to triangle VWU. Okay, so that tells us what angles correspond. That tells us which sides correspond. Now we can find the values that they ask us to find. Then you've got to prove that triangles are similar. Angle, angle, side, 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 or side, angle, side. And I'll tell you, use what's there. You can't add anything to get to a proof if it's not shown to you. You cannot assume anything. What I mean by that is problem number 10. There's only one possible proof that might work for problem number 10. It's not angle, angle, because I only know that there's one pair of angles that are congruent. I don't see any other angle measurements. It cannot be side, 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 because I don't have all the side measurements. The only possible proof, and I don't know if it is or not, I have to set up the proportion. The only possible proof is going to be side, angle, side, because these 2 angles here at the intersection of M are called vertical angles. Those are congruent. I know that already by the definition. So that's what I'm talking about, because I've seen that a lot of mistakes on the Unit 3 test, where proof for congruencies operate basically the same way. The information has to be there in order for it to be proven one way or the other. Similarly, problem number 11. There's no side measurements whatsoever. We have no side length information. So the only possible proof that might work is angle, angle. And then you have to do the work through the setting up the proportion to see if they truly are the same or not. The angles, I mean, they're going to be similar if you prove that. So all these proofs are like that. Problem number 12. That might be side, 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 but that's the only possibility. So you can't force anything on those proofs. And today we did proportional parts. So go back to those notes on how that came together. 18 and 19 are pretty similar because now we're talking about transversals, and we got a bunch of parallel lines. So don't forget, those little arrows mean parallel lines. So even though it's not triangles, the proportionality works the same because we got parallel situations. So what I would encourage everybody to do is go through that study guide. If you got questions about something, before you take the test, work some of these problems out based on your notes from today and from Tuesday. Take a picture and send it to me. Say, hey, am I doing this right? Or contact me and we can set something up individually and we can go through some of these things together.
Are the Jamboard files for Tuesday on Google Classroom?
I didn't use any on Tuesday, I don't think.
Okay.
All right, so we're really kind of out of time for today, guys. So anybody got questions? I'll double check that, Rashad, but if I use one, it would be in Google Classroom. I just don't remember doing that on Tuesday.
Okay.
All right, guys, we will see you next Tuesday, and hopefully everybody has a good weekend.
Hey Jay, I have a doctor's appointment here in like 15 minutes, so I might not make financial foundations.
Okay. All right. Catch the video tomorrow then.
All right, cool.
All right. See you later.
Thank you.